This lesson covers solving systems of two linear equations using the process of substitution. In a previous lesson, we had already looked at elimination. Now our motivation for looking at elimination and substitution as options of methods to solve systems of equations is that we wanted an algebraic method for the purpose of we want to solve systems of equation algebraically so we don't have to rely on graphing to find our solutions. So like I said in a previous lesson, we've already taken a look at elimination. Now we want to take a look at substitution. So let's take a look at the steps that we go through in order to solve a system of equations by a substitution. Okay, so here's our first example. There's several steps to follow that are common to all problems that you want to solve through substitution. So I've got my initial problem right here. Negative 7x plus 7y is equal to negative 21, and negative 3x plus y is equal to 7. The first step that you want to make sure you accomplish in solving a system of equation by substitution is that you want to make sure that you take one of the two equations and solve it for one of the two variables. So in other words, I either pick my top equation or my bottom equation, and I solve it for either x or y. Now I look at this and I see a nice opportunity with the bottom equation. I see the bottom equation as being fairly straightforward to solve for the y variable. Namely because the y has a 1 as a coefficient in front of it, so there'll be nothing to divide by. If I want to solve this bottom equation for y, all I have to do is add 3x to both sides. And that produces y equals 7 plus 3x. I now have taken one of my two equations, I took the bottom one, and I solved it for one of the two variables. I solved it for y. So I have my top equation that stayed the same, but the bottom equation got rewritten as y equals 7 plus 3x. It's the same equation, just rewritten. So that's step one. You want to make sure that one of your equations is rewritten to be equal to one of your variables. The next step is this. Substitute the rearranged equation into the appropriate variable on the other equation. Here's what this means. I have solved for y, and this bottom equation says that y is equal to 7 plus 3x. Well, in a system of equations, the x's and y's in both equations are the same x and y. This means that if y equals 7 plus 3x, which we found from the bottom equation, I can take this 7 plus 3x and substitute it in for the y of the other equation. This is why it's called the method of substitution. So when I do that, I end up with negative 7x plus 7. Now in the place of y, I'm substituting in 7 plus 3x is equal to negative 21. So you'll notice by doing this that you accomplish something that is extremely helpful in solving a system of equations. In our new equation here, we no longer have the y variable present. The only thing left is the x variable. Negative 7x plus 7 times 7 plus 3x equals 21, or negative 21. So what that means is now I can solve for the remaining variable. The x is left, so I'm going to solve for that. So doing that, that produces negative 7x, distributing in this 7 times 7 is 49, 7 times 3x is 21x. And all of that is equal to negative 21. Okay, so now finishing off solving this equation, I need to combine the like terms. That's the negative 7x and 21x. That produces a 14x. I still have my plus 49, is equal to negative 21. Finishing this off, that's minus 49 from both sides. That produces a 14x is equal to negative 70. Dividing by 14 to finish solving for x produces x is equal to negative 5. So we just solved for the x part of our equation in our solution to our system of equations. But we know that this isn't the final solution. We know that a solution to a system of equations contains a coordinate point, specifically two linear equations. It contains a coordinate point x and the other variable we have is y. So what we do from here is the same as what we do in elimination. We pick one of our equations, it doesn't matter which one, and we plug x equals negative 5 into that equation to solve for y. Now, it is often the easiest to use the equation that you rearranged and the rearranged portion of it. So I am going to use the y equals 7 plus 3x. Okay? And then x equals negative 5 is what's going to get plugged in. It's easiest to use that because your equation is already solved for the variable that you're trying to find, y. So in this case, y is equal to 7 plus 3 times negative 5. That is, y is equal to 7 minus 15. Finishing that off, y is equal to negative 8. So negative 8 is the y portion of our solution. Putting the x and y together, the final solution to the system of equations is negative 5, negative 8. So what does this mean from a visual standpoint? It means that if I were to go and graph these two original equations on a coordinate plane, the point at which the lines would intersect is the point negative 5, negative 8. So those are the steps we take to solve the system of equations by substitution. Step 1 was to rearrange one of your equations so that it was solved for one of the variables. Step 2, take that piece and plug it into the other equation so that one of the variables goes away. Step 3, solve for that remaining variable. Step 4, use that value in one of your original equations to find the other variable value. Your solution then is the coordinate point, xy negative 5, negative 8 in this example. So let's go ahead and take a look at a couple more examples just to drill this concept home. We're going to take a look at two examples and then two special case examples. So here's an example. We got 4x plus 8y is equal to negative 4, and x minus 6y is equal to negative 1. Now, the first step, as we saw above, is to take one of your equations and solve it for one of the variables. When I look at this, I see this bottom equation as allowing us to do that the quickest. I've got x minus 6y is equal to negative 1. The reason I see that is that one of the variables already has a coefficient of 1, meaning all I have to do is one thing to solve for x. I have to get rid of the 6y. I'm going to do that by adding 6y to both sides to undo the minus 6y. This results in x equals 1 or negative 1 plus 6y. So my top equation stayed the same, 4x plus 8y is equal to negative 4. But I rewrote my bottom equation to solve for one of the variables, and it turned out as x equals negative 1 plus 6y. Now the purpose of doing that, as we saw, was that now that I know x is equal to negative 1 plus 6y, I can plug this in to the x of my other equation. That produces 4 times negative 1 plus 6y. So I substituted negative 1 plus 6y into the x of my other equation. And I still have my plus 8y is equal to negative 4. but the x's are now gone. The only variable left in my equation after the substitution is the y variable. So we can now solve for that y variable. Distributing in this 4 produces negative 4 plus 24y. 4 times negative 1 is negative 4. 4 times 6y is 24y. I add 8y, still equals negative 4. Combining the two y values, which are like terms, produces negative 4 plus 32y is equal to negative 4. I'm going to add 4 to both sides as I continue to solve for y, and that's 32y is equal to 0. Last but not least, to finish off solving for y, getting that by itself, divide both sides by 32. And I end up with y is equal to, well, 0 over 32 is 0. So the y piece of my solution to this system of equation is 0. And I found that through substituting what x equals into the x of the other equation. I can now take any equation I want. Again, it's probably the fastest to take the rearranged equation right here because it's already solved for the variable that we want to find now, the x. I found my y, which is 0, so it gets plugged in here, and I want to find x. X is equal to negative 1 plus 6 times 0. Well, 6 times 0 is 0, so x is equal to negative 1. I now have both pieces of my solution. The solution is the xy coordinate, negative 1, 0. Moving on to our next example, we have a situation which is a little bit different. The system of equations we have here is negative 3x plus 6y is equal to 21, and 6x plus 6y is equal to 12. Now, some of you watching this might see that this equation is set up pretty nicely to solve by elimination. I could multiply the top equation by 2 in order to add the equations and eliminate the x's. Well, where that is true, and if I were to do this on my own, that's probably what I would do as well. I would solve this through elimination. We're going to use this as another example to illustrate the process of substitution, since that's the topic that we're on. So taking a look at this, I've got negative 3x plus 6y is equal to 21, and 6x plus 6y is equal to 12. Now I need to take one of my equations, if I'm using substitution, and solve it for one of the variables. Okay, well, I think I'm going to take the top equation, and I'm going to solve it for x. Now, none of the equations have a variable whose coefficient is just 1. So I just have to pick what I think is going to work out best. So negative 3x plus 6y is equal to 21. To solve this for x like I want to, I first need to get rid of this y term. So I'm going to subtract 6y from both sides, which leaves me negative 3x is equal to 21 minus 6y. But I still have that negative 3 in front of my x, which I want to get rid of. So I need to divide that away since it's attached to the x by multiplication. So divide by negative 3. Now, I have to divide everything on the other side by negative 3 as well, if I'm undoing it on this left-hand side. Negative 3's cancel out, and I'm left with x equals, now if I'm dividing everything by a single value, that single value can divide each term in the numerator individually. Remember, terms are separated by pluses and minuses, so I have one term in the 21 and another term in the negative 6y. So what I'm going to do first is 21 divided by negative 3 produces negative 7. And then I'm going to do negative 6y divided by negative 3. Well, negative in the numerator and denominator becomes positive, and 6 over 3 is 2, so it's going to be plus 2y. So x is equal to negative 7 plus 2y. So that top equation got rearranged as x equals negative 7 plus 2y. And the bottom equation stays the same as 6x plus 6y is equal to 12. Now again, the point of that rearranging is, now that I know what x is equal to, I can take it and plug it into the x of the other equation. So that's what I'm going to do. I'm going to do 6 times negative 7 plus 2y goes into the x, plus 6y is equal to 12. And just like in the other cases, one of the variables, the variable that I substituted in for, now disappears. So I only have y's left in my equation, which I can now solve for. So first thing I'm going to do is distribute the 6 in to get negative 42. That's the 6 times negative 7. And then 6 times, 6 times the 2y is 12y. And I still have my plus 6y is equal to 12. So first thing I'm going to do is I'm going to combine like terms. So I have this negative 42 sitting here, but the 12y and the 6y can combine into 18y. And that all still equals a positive 12. Well, peeling everything away from the y, I'm going to add 42 to both sides. That gives me 18y is equal to 54. Getting rid of the 18 multiplied by the y means I need to divide by 18. And 54 divided by 18 is 3, so y is equal to 3. So we've found half of our equation, or our solution, I should say. So we found the y value. We now, again, like the other examples, need to find the x value. Since the rearranged equation up here is already solved for x, that's the equation that I'm going to use. So x equals negative 7 plus 2y. This y equals 3 is going to get substituted in, and that produces x equals negative 7 plus 2 times 3. So that's x equals negative 7 plus 6. Negative 7 plus 6 produces x equals negative 1. So my x value is negative 1, and we had already solved for the y value, which was 3. So the solution now to this system of equations is a coordinate point, negative 1, 3. So we've taken a look now at 3 separate examples and worked through the process of what is the method of substitution to solve systems of 2 linear equations with 2 unknowns. What we want to do is we want to take a look at this 2 more times. However, in these situations, we have special cases. Just like in elimination, we looked at 2 different special case scenarios. We want to look at 2 more special case scenarios here. You're going to find that they're very similar, if not identical, to the situations that we saw in elimination. So let's take a look at those. Here's my first system of equations that I'm going to solve. That's a special case. That's a negative 3x plus 24y is equal to negative 3. And negative x plus 8y is equal to 5. Now, substitution, I need to take one of my equations and solve it for one of the variables. Let's choose our bottom equation here. The negative x plus 8y is equal to 5. And I see x with just a negative on it, so I'm going to try to solve for the x. That means I need to get rid of this 8y term, so I'm going to subtract 8y from both sides, and that produces negative x is equal to 5 minus 8y. Now, yes, I have only x on the left-hand side, but it has a negative on it. We don't want that. We want positive x equals something. So to get rid of this negative, you can think about it 2 ways. One of the ways is that there's really a negative 1 right there, so I divide a negative 1 away. which means I divide the other side by -1 as well. This produces x is equal to, well, 5 over -1 is -5. -8y over -1, the two negatives make a positive 8y. What you'll notice is every term simply changed from positive to negative or negative to positive. That's the other way you can think about it. If the term that you want to be positive is negative, make it positive, but then every other term in the equation, both sides of the equation, must switch sign as well, positive to negative or negative to positive. So we rearrange that bottom equation. We still have the top one at -3x plus 24y is equal to -3, and we have this bottom one rearranged now as x equals -5 plus 8y. So again, we achieved what we wanted. X equals -5 plus 8y. That means I can take this x and plug it in for that x. That produces a -3 times -5 plus 8y. I still have my plus 24y is equal to -3. Okay, great. The x's have canceled out. I only have y's left, which I can now solve for. Well, doing the distribution, -3 times -5 is a positive 15 because of the two negatives multiplied together. -3 times positive 8y produces a negative 24y. And I still have the positive 24y plus 24y on the outside of the parentheses equals -3. Now some of you are already seeing that an interesting situation is going to occur here. If I combine my like term of -24y plus 24y, they cancel each other out, which means that I'm left with 15 is equal to -3. This statement is obviously not true. This is a false statement. From the elimination special cases that we saw, a false statement means that there is no solution. There is no solution to this system of equations. In other words, if we were to graph these two lines, they would be parallel to each other. They would not intersect at any location. So there's our first special case. Just like elimination, in substitution, we can get a solution such as no solution. Let's look at our last example, which is another special case. Last example here, we've got x minus 6y is equal to -16, and -2x plus 12y is equal to 32. Okay. At this point, hopefully you see that the first step is to take one of your equations, solve it for one of the variables. That top equation looks like it's going to be the simplest to do that with because the x already has only one, has a 1 as a coefficient. So to solve this for x, I just need to get rid of this 6y term by adding it to both sides. And that produces x is equal to -16 plus 6y. So x is equal to -16 plus 6y is the rearranged top equation, and -2x plus 12y equals 32 is still in the denominator, or in the bottom equation, not the denominator. So again, this allows us to now take what we solved for x and plug it into the x of the other equation. So x is equal to the -16. Oh. Let's go back there. We jumped up on accident. There it is. So x is equal to -16 plus 6y. That's what goes into the x of the other equation. So that produces -2 times -16 plus 6y, and then I still, in the parentheses, and I still have plus 12y equals 32. So doing my distribution to solve for y now, negative 2 into negative 16 is a positive 32. Negative 2 multiplied into 6y is a negative 12y. And I still have my plus 12y equals 32. Now something similar, but not quite the same, is going to happen in this special case as the previous one. We see that the negative 12y and 12y are actually going to cancel each other out when I combine those two like terms. And what am I left with? 32 is equal to 32. Now, this is a true statement. 32 does equal 32. Well, when the variables that we're trying to solve for disappear, when they're eliminated, but we still have a statement that is true, this, as we saw in the elimination lesson, means that there is infinite solutions. What this means is, on a coordinate plane, these two lines are right on top of each other. They share every single point. So we can solve systems of two linear equations, also by this new method, the method of substitution, where we're taking one of our equations, solving it for one of the variables, so that we can substitute it in to the variable in the other equation, thereby creating a situation in which only one of the two variables is left, which we can then solve for, and then use that and solve for the other variable by using that solution and one of the other equations. So that's the method of solving systems of equations, specifically two linear equations, by substitution.